So good afternoon, everyone. It's fantastic to see you all here, and a real pleasure to be stood here at the moment. What many of you don't know is that organising this seminar was actually an incredibly brave thing of Alexandre here to do, given that he had his PhD Bible yesterday, and Helena here was his external, and so if he hadn't passed, so congratulations, Alexandre. If he hadn't passed, this seminar would have had a very different flavour. It wouldn't be here. So that leads me on to introduce Helena Chum. And I've known of Helena and known Helena for all my research, all my active postgraduate research life. And Helena comes with an aura of, how do I say this, an aura of leadership in this area around bioenergy and the bioeconomy. It's not just an aura. I don't know anyone who works so hard, who's read so much, and who's produced so much in this particular area. Helena is also one of these very unusual people who has a very distinguished technical development background. She's heavily involved in developing underlying bioenergy conversion systems, but also has worked through to a really stellar global reputation in policy and development of the bioeconomy and bioenergy in particular. I think it's fair to say that the kind of seminal piece of work Helena was the International Intergovernmental Panel on Climate Change's special report on renewable energy, which Helena was the convening lead author and was published in 2011. And for those of us geeks in the bioenergy area, that was really a seminal report leading through into the fifth assessment report and the coverage of bioenergy in the fifth assessment report. And bioenergy continues to be an incredibly controversial topic. In fact, I would think it's fair to say the most controversial topic in the mitigation, adaptation and science sections of the fifth assessment report. Helena is one of 10 research fellows at the National Renewable Energy Laboratory in Golden, Colorado. And Helena, I'm sorry to say that in my family, you're not the most famous person from NREL. I'm afraid that accolade goes to Dale Gardner, who, of course, is an astronaut. So I'm sorry,
That's exactly
he's a man
right.
who's been on the space shuttle. But apart from that, you're right there next door to that. So Helena is going to talk to us today. She's going to give us a presentation on the role of the bioeconomy in climate change. I think, 4 or 5 years ago, that would have been bioenergy. But Alexandre's PhD thesis and much of our work in the Centre for Environmental Policy here in Grantham in the Energy Futures Lab and in Climate Kick has highlighted the need for us to understand bioenergy in an integrative perspective within this bioeconomy, this kind of new buzzword, although it's not that new. And so it's very appropriate. The title of your talk is very appropriate. I have a few housekeeping things which I nearly forgot, Alexandre. So this seminar is going to be recorded, and at the end I'm sure you'll all want to ask questions, and when you do, you need to ask the questions with this microphone on so that can be recorded as well. For those of you new here, there aren't any toilets in this particular building. You have to go out and through into the electrical engineering building just over there. There's no planned fire. But should you hear a fire alarm, we all go out in a very orderly way out through those doors there. Right? And to the Queen's Tower. Helena's going to talk for 50 minutes or so, maybe an hour, and then we'll have half an hour of Q&A, and coffee should hopefully magically appear at around about that time with some biscuits. So Helena, absolute pleasure having you here, and over to you.
Thank you very much. Thank you, Jim. It really is a pleasure to be here. It's very nice. Jim didn't mention, but I was born in Brazil. I don't look Brazilian because my father was Chinese. But then my husband was American, and I had this option. Do I move to the States, or do I bring him to Brazil? Couldn't, because he couldn't speak any Portuguese. So I moved to the States, and My first job there was in the Solar Energy Research Institute that a few years later became the National Renewable Energy Laboratory, in recognition of the world-class work that we were doing in several renewables area and energy efficiency. That's the difference between this laboratory of the U.S. government and the others. The others are multiple programs or security, nuclear, and things like that, science. And we really were created from the beginning to try to take renewables and move them to the marketplace. So that has been a pretty big difference between the lab and the others. So the science was always been looking at the applied side and trying to move the applied side into the market. So that has been a very interesting origin. And the areas that I'm going to talk about, you're going to find, okay, this is not, I probably should. Okay, I'm going to mix a little bit of the special report. Principally, some of the controversies, as Jem mentioned, controversies were, one, how much biomass is there? Two, does it do mitigation? Three, is it sustainable? The following, why did we have to come back? And I had to come back into the fifth assessment. At the second assessment that ended in 2011, the number of publications between 11 to 13, 14 around life cycle assessment of bioenergy and all those areas had increased enormously. And in the special report, the chapter on bioenergy was very balanced, talked about the positives, the negatives, but the chapter on sustainable development was extremely negative on bioenergy, and the points of view were coming from different aspects, one from the bottom up, the other from top down, and the modeling actually required a lot of bioenergy. So the chair, the co-chair from Working Group 3 then said, well, we don't have a link between the bottom up modeling and the top down. And it's true. At that time, there was very little. There's a little bit more yet, but we're not yet where we need to be able to take into account all of the important phenomena linking top down and bottom up. So I'll run through some of the potentials, some of the mitigation, some of the other environmental aspects, couplings with fossil, for instance. And I'll talk a little bit about challenges and opportunities. And one is the sustainable energy for all the UN goals and what they're trying to do, which is very interesting. It's to double renewable energy, double the rate of reduction of or introduction of efficiency, if you will. And then third, basically provide access to all. So in terms of putting more bioenergy instead of traditional biomass, or changing the system so that there is access that's universal. And we'll talk about that. Those are pretty challenging goals. The bottom line, I think we're really at the point of talking about transforming systems. And how do we go about that will actually have a big impact on whether we can actually use bioenergy where it's really very appropriate. And it's something that over the years, I've always been known for, oh yeah, we can make power, we can make fuels, we can make chemicals. I've been always tied to pulp and paper and agriculture, so I could always see there's a big range of things we can do with biomass and should do. And it's a question of where you are. So it's all context dependent. And so you had factions developing over time. No, it should be just fuels or depends on where you are. So to try to get people to understand that has been actually fascinating. This is the point of the SREN, where we had at that time, 2008, about 50 exajoules from biomass as primary energy. The numbers that are well known, these are relatively old, they've increased somewhat. Less than 250, so 240 exajoules is, if you took all the food, the fodder, the fiber calorific value. And at the time, the primary energy was about 500, so about 10%. The panel, looking at a number of different reviews of literature, we actually concluded, and people actually didn't understand, but many of the work that the group of Underfied in Utrecht at the time, they actually explored scenarios that went all the way from 0 to 1,500 exajoules. For us, the 1,500 exajoules was the quote-unquote theoretical potential. And in that case, they had less protein than you have in your extreme scenarios, okay? So then they would make more and more land available for protein from animals, and then 500 was one that was well documented, but the panel was between 100 and 300, more towards the lower side, as potential for deployment. Okay? How do I go back? I better go back here. I have to escape first. I'll better use the other one. Yeah, escape, yes. Let me go back. Yeah, that's great. So these numbers were actually quite well modeled by the many, many scenarios that were run from, but not all assumptions were independent. So it's really difficult to say that every model counts as a model, but it's a collection of models. So they presented a range. In the range of all scenarios, in some cases there were 64, in some cases there were 100 scenarios. And for detail, full economy, unfortunately there were only few. The same thing happened in the fifth assessment report. But from the range, you see that for a level not so good, or 450 to 600 ppm concentration, the 75 level, confidence level, 25 to 75, was 80 to 150 exajoules. But the max and min were between 20 and 265. If you went to a much more strict mitigation level, then we had 120 to about 190. So this 80 to 190 was not far off from the numbers that the panel felt could possibly be deployed. And if you look at the global energy assessment, their different modeling activities had a range of 80 to 140. And there has been a lot of controversy because the bottom-up, exactly the type of thing that Alexander did on the thesis, which is to look at lands all over the place and try to really do scenarios that model from the bottom up to try to assess how much bioenergy could be in various types of applications. And that's what's very, very interesting about what he has done. So here comes the controversy in some of the reasons. In the Sustainable Development chapter in the SREN, they had a lot of people who came from this perspective. And we had a lot of technology people in the SREN. All of those were brought together to look at it again in the fifth assessment report. So immediately you can see that there will be several opinions, and all of them based on very reasonable assumptions from their point of view. So Harborell and co-workers and colleagues coming, really looking at the human appropriation of net plant productivity, looking at potentials that could expand production, their conclusions were that the blue parts of potentials would be the likely ones. Then, if you go to, we had probably many of you know Edgar Hertwig. Edgar comes from a life cycle perspective, from an input-output life cycle perspective, looking at resource productivity, materials productivity. So those folks are looking at, well, how should we actually look at designing all the systems, biomass and all others, so that we have not only good climate impact, but also excellent material productivity. So those would be higher, okay? I think I put myself here. I'm trying to see, can we actually design systems that combine in a certain place? Because where you have biomass, where you have that need for sustainable development, you can actually design a system that allows them to develop and use their biomass and others, and maybe really not leapfrog where we do development, not follow what we have followed in the developing world. And then the technology optimists, of course, they would go fairly high. But that's the reason, and they are valid reasons from points of view that are all of those justifiable within that type of view. And I'd like to bring this up because it's a European, I don't think anybody else has done this, okay? But that is to take 2,000 kilograms of a basket of products that you have consumed, okay? And assume that consumption is proportional to what you're going to contribute in terms of greenhouse gases, and it's going to be proportional to the contribution of this materials flows to an environmentally weighed material consumption. What this means is taking all of the air emissions, soil emissions, water emissions, rolling them. And the way that they roll it is not one that's accepted. It's an European accepted method. The folks in the US don't like that because they group certain categories of impacts together. And we prefer to take all of them and then do the analysis, and we're moving in that direction by doing just basically a multi-objective analysis with all of the data without discarding anything, and then coming at the same kind of one number. That's moving. But as you can see, the fossils, okay, really do in fact have the largest contribution. I didn't realize this guy is. I can't touch it. In the greenhouse gas, but not as much on the other environmentals. And in part because those big oil refineries are concentrated in a few locations. And they're really highly regulated, so you will have a very tight system. Now, if we look at the animal products and the crops, and this purple here is the forestry. The forestry here looks very, very small, but in the biodiversity part, it becomes very large. Okay, but the biodiversity not as much appears here. But the animal products, which contribute to greenhouse gases, also contribute in much more to environmental degradation. So that's the rationale of that second line that's looking at not only do I want to minimize issues relative to climate change, but I also want to improve this. And the crops the same way, there's room to improve. And the inorganic products, even though there's a lot used, don't seem to, from this analysis, to do a lot of harm, relatively. Important here to say is that this is what the EU makes and imports as well. Okay, so this is taking the consumption, all of it, aggregated. So those are interesting lessons. Now, I mentioned the UN Sustainable Energy for All, and it's very important to understand where biomass, and I think they are looking at it with an interesting way of showing. Okay, we have this traditional biomass, which actually is low efficiency combustion that's practiced indoors, in stoves, in developing world mostly, where the efficiency is low and the amount of pollution to the air is extremely high. So that is something that we need to decrease. So now biomass combustion, well done, like done here in other countries, now that's very, very highly automated. The pollution is very well controlled, and it's very high efficiency. So we need to decrease the amount of this, provide the same services or better, heat for as biomass for, and then for industry. It can be combined heat and power as well. Heat for district heat buildings and other kinds of heat direct, biogas, biofuels for transport, power. So the biomass is actually really pervasive in all of the uses and power, heat, and fuels. And the other renewables, you can see what they are penetrating right now. And if you look at the remap 2030 is what IRENA has developed with a number of collaborators from industry, academia, and many different types of government and associations to try to see how could we actually double the share of renewable energy, double efficiency improvement rate, and then get the universal, and they analyze obviously investments and stage of development. So those materials are all well documented. And one thing that's quite interesting, they looked at the jobs. And if you look at the jobs, liquid fuels was 1.4 million jobs. The biomass, power, heat, 0.8, and biogas, 0.3. That's 2.5 million jobs. All the other renewable energy technologies were 4. So that's a pretty large amount of jobs for this particular group. And that is the specific report. If you take the other report on the manufacturing sector, there you will find how much of the renewable biomass could actually contribute as a feedstock for chemicals. And the quantity is quite large. It's 2 exajoules that they are coming up from the analysis as being possible. Biomass is actually very flexible, but we have this range, and many people say, well, it's not working. I think it is. Actually, it held the growth, okay? We had a decrease of the traditional biomass over the recent past, and in many places, this is a 1 year in Peru with a very decent looking kitchen, and people adopting just, if you do the right thing and you put the right technology, even this example in India is a very interesting, this is from the Global Cooking Alliance, where they found that the new ways were even better for for the flavor of the food. So you can do things to paying attention to that. So biomass goes all the way from the household to the communities, municipalities, and has a range of industries, suppliers, and users. And then, in addition, beginning on the distributors and consumers. So this 35 is the tradition, most of the traditional biomass. The 4.8 is the transport. And this is a snapshot of what they were saying that they would like to see. So you have a snapshot of 2000 and 2012 and what the growth factor was. And you see that the growth factor is nearly 6 for the transport, 5 for the pellets and chips and so forth. For cogen was a factor of 3. Traditional biomass decreased. Power increased by a factor of 2.4. What were the governments planning? The governments were planning for 2030 these numbers, where you would have a total of biomass for fuels and power of 29 exajoules. This remap 2030 would like to bring that to 108. So that's the kind of, so that would imply even a bigger growth. But this would actually lack a target of 20% of the primary energy from biomass. And without the biomass, they couldn't get all the rest of the renewable energies to penetrate. So that was required to reach this factor of 2. It's a lot of growth. So just a reminder, chemicals and materials play a very important role, and that part of the industry is moving extremely fast. Okay, and in some cases it's moving fast because the properties of these materials are superior. So they're not only just targeting substitution, but they're targeting, let's make newer molecules. They did a job of trying to really look at the land availability, so the supply and the cost in the various areas. What about the greenhouse gases? So I'll take an example of the IPCC, and for Edgar's dissatisfaction, actually my dissatisfaction too, we had a lot of data on biomass, a lot of data on various systems. You go and try to find that for the traditional coal and try to find that for carbon capture and storage. The data are really not very high level. And in fact, we have a lot more data that has very substantive inventories. And that the same is not applicable to many of the fossil technologies. So it was really a difficulty to try to put something like this together. The other thing we wanted to do, which became possible because more data, biomass to grow for 5 to 10 years, that's what you have to wait until you get the data, to look at numbers like how much soil in the carbon when you make a transition, how much a kind of management system, the no-tillage. You have to study years and years and try to come to conclusions. So at this time, this is what we did. In the various examples, we separated from various references. Here are the ranges of soil organic carbon. Here are the ranges of biogenic CO2. Here's the ranges that you could store, okay, if you used, for instance, switchgrass in combination with carbon capture and storage, assuming the carbon capture storage data are reasonable. Okay, so the net values would be here. If you don't have, CCS would be here, around the 20, and then they could be sizable values, and then combined with fossil, then this is a significant decrease, much more than what you get with coal or natural gas IGCC. But the other part is the versatility to do, if you do gasification, you can do the biomass to liquids or coal and biomass to liquids. So those two are numbers, and we would love to have more data, but more data on the integrated systems. In the CCS case, I've seen, for instance, now additional data from the large ADM demonstration on the injecting fermentation CO2 in the Illinois Basin, and that at a fairly large size. So that is going to continue to produce numbers, and they're also going to couple the CO2 from the power plant into the same formation. So we've had in the US an enormous amount of enhanced oil recovery data, so the transport part reasonably covered, but not as much life cycle data, and the monitoring is continuing. So one option, principally if we need to decrease very quickly and do not start soon, one thing that the scenarios try to do is look at other options. So you could do hybrids with gasoline, you can do electricity, or you can do hybrids with biofuel as well. So you have a number of data like that. What is one of the things that's most difficult for the category of agriculture, forestry, and other land use, which is where all biomass is, and all forestry and all agriculture, is the uncertainties. Okay, the measurements are very difficult. But this is actually a very good sign. Of all sectors, this is the only one of the economy that decreased. Every single other sector increased. And what we are now is really trying to make sure that we actually measure well. And there's no way that discussions can exist, and some of the uncertainties in some of these numbers are very high, but many of the countries do not yet provide all of those data. Some of the methodology needs improvement, but I think it's working towards getting to the point we can measure reasonably well. Because remember, you have carbon retained in the soil if you appropriately do the management. So if you can measure all of this well, and even the amount of deforestation in some regions has in fact decreased. And countries like the US has increased significantly the amount of forest carbon from third generation or regeneration of the forests. So this is good news. We need to try to make sure that we measure, because there's nothing like the measurement to try to actually make folks comfortable with the idea that you can in fact store carbon. And I'll give you one example. And these numbers in the bottom are the number of scenarios. And the mitigation efforts that we're talking about, they really are throughout the economy. You cannot do anything. You can just work with one sector. You actually have to work with all of them. And depending, if you actually can decrease the demand of electricity, for instance, you might have more flexibility in how you do it. But you see the various sectors: transport, buildings, industry, electricity, and this is the net agriculture, forestry, and other land use. because the agriculture, forestry, and other land use have emissions and have sinks. So the sequestration that that sector does has to be subtracted from the emissions, and what we're looking at is the net value. And so this is the net value. This is the net value in case you cannot do carbon capture and storage. And Jim and Alexandre look at the numbers, -15, -12, okay, gigatons of carbon dioxide equivalent per year. That's what they would have to contribute if CCS cannot be developed. So I was very pleased to see those levels in his calculations. And then if you actually, but look at how all sectors have to contribute. The baseline, look at where the baseline for electricity would go. So those numbers are really very, very high. Now, with CCS, that biomass would be the same amount of biomass, but in different technologies. So direct and also with CCS. Those are the non-CO2 emissions. So all sectors have to contribute. Now, one thing that's important here, let me come back here, is that unfortunately, look at the number of people who can actually deal with the biomass portion. Okay, that's why we need additional data, and why I was so pleased, because we have now one additional tool to be looking at how the FOLU can be a contributor. And these numbers so are of much less quality than the others, but not many of the scenarios could do all of the areas. So how much low carbon technologies? If you have a high energy demand or if you have a low energy demand. And you can see the numbers for biomass they are maintained with and without. The ranges change somewhat. The amount of solar, obviously, in the high energy demand would be much, much higher, but this is still pretty significant. Wind, geothermal, hydro, these numbers are similar to the SRR-EN. Again, nuclear, non-nuclear, nuclear growth, and gas and coal with CCS. So that's an intermediate scenario. If you take one scenario where people can do a lot of differentiation, and this is an example with the GCAM, if the CCS is not available, biomass is much more valuable to reduce emissions in transport than in power. And when CCS is available, it's the other way around. So you can see here the example of the electricity here. Without CCS, you have nuclear having to become a fairly large contributor, right? Wind to become a contributor. Biomass will go into a transport. Now, the transportation fuels, you'll see the biofuels with CCS. Biofuels, CCS doesn't exist, so it's biofuels that does the biggest target of the transport fuels. And if I show you the other example, there are many others, but here's where you do have CCS. Then, in this case, the transportation fuels is a small slice, but the CCS, the biomass allows CCS of coal and others to continue for longer because it can offset those emissions for a longer period of time. And this is sort of been similar results in other kinds of assessments. Why is it that this is such an interesting time for bioenergy? Science technology has done such a, it's amazing how much progress there has been. And what we are seeing is the ability to go beyond ethanol, beyond oxygenates, and go straight and reproducing the fuels that exist today and the mixtures or individual compounds, depending on how, where you are. Why I think that's important? I think that's important because there's no way that if we take aviation fuels or even some marine fuels that we can put oxygens in it. It has to be hydrocarbon. And it has to be basically the same type of composition. It has to be a mixture because you put that line across and you have specific compounds that have properties on the little rubber interconnects into different parts. So it's a very complex system where your ability to influence, or if you actually do some change that loses properties or performance, you have a big problem. So I think this part, oxygenates continue, ethanol continues where it is appropriate and infrastructure is not that available. It's possible to change that infrastructure more easily. But here, you don't really have the many degrees of freedom. So there's been a lot of efforts to do the technologies, and there are many technologies that are pursued that are, in fact, being tested in planes. All of you have heard about many companies and many partnerships that are testing those. The other thing, there's been an enormous amount of sustainability activities across the supply chain. I'm showing examples in the United States, the examples in Europe. There's a large number of examples there too, where you have the feedstock production and logistics. If you're going to continue in a large-scale mode, and you have to go beyond what we have now in operating in the United States, which is about 700 tons per day. But if you have to go to 4 times, 10 times that amount, then you have to develop a different infrastructure and make intermediates that are densified, pelletized, or torrefied, or there's got to be some kind of an uniform feedstock, more uniform feedstock that can be stored for a long time, and silos like the corn silos. Some corn plants are size of relatively small, not too small, refineries. So there is people working here, a lot of work minimizing GHG, minimizing pollution, maximizing efficiency, a number of products, and use looking across the impacts in an integrated way. So water, that's another very important feature, and we are, as the World Bank is, looking at scenarios that are very good, putting all of those things together, looking at watershed by watershed, so spatial temporal resolution, looking at best management practices, and actually even convincing some of the corn farmers in the United States that there are regions where they're fertilizing a lot, they have no yield. They shouldn't be doing that. They should be planting some perennials around. So we're trying to do landscape planning, management, and water, as well as nutrient management in a pretty broad way. And I'm really pleased that the tools that they have developed in terms of, well, if the farmer has a yield of such and such and they understand the soil, the programs that can actually look at past yields and current, what does it look now, and actually tell the amount that they can take out that's not going to make it difficult for productivity of the following years. So those are being tested. A combination of the USDA and the Idaho National Laboratory have made the tools. DuPont is testing it in their refinery. But we've actually forced everybody that was part of those big demonstrations to look at all their sustainability, all their feedstock supply, do measurements, so that we would be able to then be able to say what level of sustainability those systems have. And the farmers that have seen now some of the maps, and they say, yeah, you know, this is really not a good yield region. And we go and say, well, look, let's design this all around this area. You don't do that. You plant something else. And from time to time, we can do harvesting of that material. Recovering the nutrients, that's the example. We had farmers around this area and showing to them that there was a lot of pesticides running and nitrogen running and so forth. And I think this is moving in the right direction. And the U.S. has had some progress. If you look at the water flows and what the hypoxic zone in the Gulf of Mexico, that's trending down. And also important is if you look at the corn to ethanol process between 2001 and 2010, the conversion process tightened up fairly well. This is less than half of what the gasoline is. And the feedstock is what's higher than the gasoline impact. And the states, this is the range of producing states. And this range became so large because many states that weren't very good producers decided to produce. But that only means the states probably will stop producing. But there has been a good effort. And this is one of the hard numbers to get, but those are very serious tests on human health cancer impact. And at this point, with all of these uncertainties, those numbers are the same. And those, in terms of potential of direct carcinogenic contributions, the same is happening for the ecotoxicity relative to waters. So we have a very substantial amount of power, and the power is very much depending on the region where you are and what type of technologies that you're putting in, what types of feedstocks that you have. This is very interesting because we were talking yesterday about the landfill program. See the landfill program over? It's been actually quite a success in bringing, and this is in fact, we're trying to get the animal, basically most of the manures, that's kind of hard, but the success here is actually quite good. And you see all the sugarcane areas, the bagasse parts, and that has been a major success in Brazil. The last 10 years, they've actually become a very important source of electricity. I wish they had more because that happens to be available when there's a lot of drought in the north part of the country. Also, global progress in commercializing liquid biofuels. For instance, this is the Gran Bio project. The Gran Bio project is actually very heavily related to the Italian Crescentino project, twice the size. Okay, and the difference here is that they are doing not just bagasse, but they are doing mechanical harvesting. So they have bagasse and more ability to make electricity. And they set up a nice system where they have the electricity production. It's another company, and so that's moving. The moving in terms of liquid fuels here in Canada also is a methanol plant from municipal solid waste. I'll talk a little bit about it. There are in the U.S., we have at the moment the Poet Abengoa, and we have the DSM Poet and the Abengoa, both plants opened. And then the DuPont will be opening next year. And all of those have a very significant amount of feedstock reliability supplies. It took 5 years to set up the supply for all these plants. And most people don't realize, and they say, well, how come it takes so long? And if you look at what is necessary, they had to have the farmers who wanted, they had to have the mechanical, the harvesters, and all of a whole set of parties that all agreed to do this. And it takes a very, it was 5 years in that case. Gasification. People say, well, gasification biomass isn't that much. Well, I think 75 plants using biomass is not so small. Okay, it's just that it is across a large number of different applications. But there are reasons why the gasification hasn't gone as fast, because it's very much harder to go to the larger scales because the investments are very high. So the risk is very high. So I tell government, yes, the risk is very high. You have to help if you want to see the benefits of all the other things that it can do. The scale opportunities, I'm really very glad to see that right now, yes, we need the large scale, but that we are also finding ways, and the success of the microchannel type reactors in being used in the stations, the platforms for the small amounts of gas to convert. That's a very good story of what can become a small scale plant that can be made, basically mass produced. And this is what you need to have for the small systems. The hurdle is to have enough projects to get there. Irene costed the number of those systems, and they have come to conclusion that actually they can't, and we couldn't, distinguish costs between thermochemical and biochemical. They are all within the same ranges. If you have a differentiated location, you might, because of feedstock cost in a specific place, but in general, it's really not possible. And so their qualifiers, they do have to deploy faster because we need to show process stability, reliability, availability, production costs to fall so that it could get to that point where you can reduce capital costs. And it was a pleasure to see renewable diesel, which is the US name here, probably would be hydrotreated vegetable oil. That industry showed up in the last 4 years, 5 years. Today we have it at 0.12 exajoules. Diesel is at 0.8 exajoules delivered fuel. Okay, so this is very, very fast development in 4 years. So we have had technological valley of death, many different companies, many different processes, many different architecture or designs. Then the commercialization issues and risks. So this is what we have seen and are trying to work through, and it is important to proceed. Now, I said that the bioenergy is really a whole bunch of systems. So this would be a pyrolysis system that the char part is a biochar that has properties that are really very good as a fertilizer or as an organic medium for plant growth. We have the pleasure to see New York at this point having biochar on the rooftops, and they're building greenhouses over there so that they can actually have vegetables and sell vegetables. So urbanization. And what's interesting for me is if you take the California, this is for California, what this biochar value would be, and you see here the applications for grapes are here, grapefruit, the landscapers, those would be lower, but the higher value would be in applications where they will need a lot of help, because those are the regions that are going to be impacted by climate change. So we need to think about agriculture adapting to climate change, and it might actually be able to do it, adapting and mitigating a bit more. So at the moment we have strong programs looking into adaptation, and I'm hoping we can marry adaptation and mitigation so we can do a good look at the overall system. So right now, the pyrolysis setups, we have already several companies producing biochar, and from the liquid, some are actually replacing heating oil. Heating oil is part of the RFS now. So there's a lot of interesting opportunities for multiple applications. And examples of some of that biochar in grasses and in basically herbs and tomatoes and so forth. Having fun looking at where technologies are. I think there's a lot of movement and a lot of additional movement that is going to continue. And I think the renewable diesel is a good example of something that's moving. It's moving relatively fast. The challenge that we have, really, how can we increase the sustainable production? The logistics of the biomass supply to the facility that's going to do the conversion, making all products that we need integrated with the specific context. And if we can do that, we have to do economic context, environmental, social. How can we do the adaptation of agriculture and forestry to climate change and foster resource efficiency, climate change mitigation in all of those, while maintaining and improving ecosystem services? So those are some of the challenges we have ahead. And with this, I think I'd like to thank you. And actually, I forgot I was going to end by putting a photograph of the National Renewable Energy Laboratory, which some of you have visited in the past. But today is a huge campus. We have 3 buildings now that actually are our test proof of a concept of net zero energy buildings, where everything inside was built. So I'm restricted to how many kilowatts I can have with a computer screen. So we sized, everybody has to have a certain, but people don't complain so much about that. It's all day lighting. The windows have electrochromic windows, so we can control. There's a lot of development that went into doing that in the campus, where you can actually have a very, very low energy building and a lot of integration of various renewables. So with that, I thank you very much for your attention.
So, Helena, thank you very much. And we've now got 25 minutes for time for questions. One thing I forgot to say, Helena, when we started, amongst many other things, but this whole session is kindly hosted here in the Grantham Institute, but is actually a combined session with the Energy Futures Lab
Right.
and with Climate Kick. So I'm pointing over there towards where Climate Kick is and where the Energy Futures Lab is. That's quite a rare activity to have a three global institute seminar. So thank you to the Grantham for hosting this, to the Energy Futures Lab and to Climate Kick for hosting it. But you covered an enormous territory in your talk, Helena, and thank you very much. It's really a tour de force of that activity. So, questions?
Yes,
If you don't mind holding it.
yes, I'm Mr. Bonfa, and I'm involved with European Union on, let's say, designing and implementing cohesion policy. One area is bioeconomy. So what I will be interested in, if you can, let's say, spend some word on the, strategy point of view, because you end with saying that you need an integrate with specific context. Now, in Europe, we have a policy now, let's call it smart strategy specialization. This means you need a strategy, and then you need a specialization, a product, where you can link with strategy to be more sustainable.
Yes.
And that's what, if you can spend some word about this one. And second, about data. Do you have any, let's say, we are interested in exploiting the data satellite for the bioeconomy. If you have some more about this. Thank you.
Thank you. I have one. And I think the bioeconomy developing here through the platform is actually moving in a very nice direction because the European program has actually focused on the higher value products. So you have at the same time a number of strategies that are all higher value and, interestingly enough, not necessarily very large volume. Okay, so I like both. And I think for the European context, where you have some countries with very strong chemicals production, the move to renewables for chemicals and materials is extremely important. So that actually helps pave the way for making it easier to penetrate in fuels. So that strategy, and I'm seeing it and talking with various colleagues in various areas, there are several pieces of strategy. And there's about 400 to 500 companies in that space already that are actually dealing with doing that part for themselves and in groups. So it's not all very public information, because as those groups form little strategy areas, they will not talk openly about everything. But the partnerships are all across countries. So a lot of the European partnerships include Brazil, include the United States, include other countries. And I think so if you have a few of those starting to penetrate, that is, and it's multiple pathways. So you have folks really trying to target some oxygenates that are, and you see I think the more weight you can maintain of your intermediates, the better off you are.
Concentration of activities.
Concentration of the mass, even, and concentration of activities as well. But for instance, we have a lot of derivatives that degrade the oxygen and degrade the carbon. But you can go to the acids. You can go to intermediates that have higher masses. So for the chemicals, you don't need to go down all the way to ethanol. You can do that in Brazil. You can go to ethylene, or you can go to a few of the other alcohols and go to propylene and butylene where it makes sense. But in other cases, you can stay with a higher proportion of the biomass as an oxygenate. And here's the interesting progress I'm seeing. People developing one-pot synthesis that are much more selective to a variety of different compounds. So this is where you're seeing a few different strategies coming up. And for instance, the current strategies, the AMR strategy has a lot of carbon and hydrogen, but has lost a lot of mass. But it's this one where you have interesting products coming up at the other end. So those refineries will move, the coatings will move a lot of different chemical products first, and then fuels. So it's a very interesting time for connecting the research with, and having the critical mass of people who can actually explore them is extremely interesting. And it's happening in Brazil, it's happening in the US, it's happening here, in several other countries too. And I forgot one.
Oh, the data satellite, but it's not
Yes,
the biomass. Yeah.
And that, I think, is being helped, or let's put it this way, IRENA has as a goal to try to get that mapped all over the world. So we've been helping a little bit, but that's essential.
Yes, thank you for your presentation. It was really interesting. We've got a project looking at production of renewable aviation fuel, specifically sort of a kerosene analogue. And most of the sort of techno-economic assessment suggests that most of the supply chains that you can think of, in if you take an average context, are just simply not going to be economically viable. In some cases, for example, taking vegetable oils, converting that into aviation fuel, your starting material is already more expensive than your product. So some of the partners that we're working with are very interested in understanding where the niche opportunities might be for local scale production, those local contexts that could fit that particular supply chain and technology. And I was interested in whether you had any insights around where you think would be the best place to look.
Well, it's actually that's an interesting question that some companies may in fact start exploring. Even in Brazil, you have some areas where you have some oils that are potentially there in many different regions. So to have the oil move to a more or less centralized facility and distribute the fuel products, you don't have to go to aviation fuels. You can go to diesel and gasoline and do that at that local level. And it would save a lot of actually transporting gasoline, diesel, and so forth from, okay, because the example of Brazil is one that we are going to have this system and the system everywhere. They abandoned the idea that you could use the local resources. So they did away with biomass power. They did away with just about everything and went for a centralized system for power, centralized system for fuels. And there was a place that could have kept, I understand why, but so these opportunities are things that can be explored. And where you have sugarcane is one opportunity, but where you have oil plantation, that is ideal. And there are a few others, but it's very much context dependent. One of the companies looking into the small scale effort as an integrated project is at the Cool Planet. I don't know if you all have heard about that, but they're trying to go straight from the vapor phase or the liquid phase and into an upgraded material, which would be in the gasoline area, gasoline diesel area. And the char and the system would be coupled to the regenerating degraded areas with the biochar. So you could have a closed circle kind of concept. Whether we can make the smaller systems, we helped develop one which is actually moving in the right direction, but it took 10 years to get to 40, 50,000 hours of operation that you need. So those are the kind of hoops that you have to do. Now, the reason why people are looking at the used cooking oil and looking at greases and fats and so forth, those will be lower cost for a while if you can get the chain to be really very effective, then that's the key message.
We have time for one more question, and then we'll have coffee. But Helena's
We
going to
can
stay
do the
around
questions,
for
sir.
till at least 3.
We can-
So we can. Okay. So, sorry. Oh, let me give you this.
Thank you. You talked about
Could you introduce yourself?
Robert Whitfield from the Seawater Foundation. You talked about feedstocks. Clearly, you talked about land and water. You talk about sustainable production. We all know the problems of first-generation biofuels and some of the ways of not to do it. Do you not think that in addition to pursuing all the things that you're describing using freshwater plants, that in fact we should look outside the box of using farming land and using freshwater, and also consider using land that has not been used for farming because there's no fresh water, and using that with salt water, seawater,
Yep.
and growing halophytic crops?
Yeah, and in fact, it is moving. I didn't have time to cover all the areas, but that actually is moving, and there are many examples of halophytes and experiments going on in that area, and concepts coupling. Masdar has some of the concepts that are going on. We actually helped a little bit. We had a person station trying to help them start that project, and I think it's very valid. And the aquatic part is interesting. It has a lot yet to go but you have some heterotrophic organisms that have interesting capabilities. So the one issue that we have had in looking at all of the, as we've had a chance in the scope, one of the activities we're doing is we've had many pilot plants moving to commercial before the time, and many developments that didn't do enough pilot plant work. And that has been a detriment. So it's important to actually do the development with all the stages in a certain order to avoid reaching the commercial stage and have a lot of other problems in the large scale. So we've lost some plants in commercial scale that just couldn't operate. So when we go to that area, and there's quite a bit of a program in the US about that, and we're doing all the mapping of where you could have them and in the two sides, and even bringing water from the ocean. So all of those are being looked at, and you have to pay a lot of attention to the not just the economics, but in the regions where you would put that, you might have, like we have a lot of hurricanes, we have a lot of, so you have to overlay all the other conditions that wouldn't be normal for, so those are all things that are under consideration. And I'm hoping we have some very bright engineers that might help.
Fantastic. Thank you very much, Helena.
My pleasure. This is a great audience.
So as I said, Helena's not going to rush off. She's going to keep
No.
here, so with more shy ones amongst